Good afternoon, everybody. Welcome to, I think, the second last talk. I'm Thilo from ZHW. We work on a lot of diverse use cases with deep learning. And while doing so, we see a lot of different things, a lot of things that are distracting from the project goal. And sometimes these distracting things turn out to be real gems, real interesting things. In the next 20-25 minutes or so, I want to take you on a journey, what we learned while watching our machines learn, so to say. There are a lot of such cases, and I picked for you two for today. One is more from computer vision, has implications on applications like, for example, automatic quality control, predictive maintenance, and so on. And the other one is from the reinforcement learning sphere, and directly a case where we worked on train rescheduling in mobility. So without further ado, let's jump into the topics. I told you we work on a lot of diverse stuff using very similar methodology, namely deep learning. You see here some things we've done in medical imaging, industrial projects, biometrics as well. There are a lot of others. And one thing you see here is that they are very diverse. The input images you see here, they look completely different. And at one point, we wondered, well, when we select a model a baseline to morph into something that really works for the case, is it actually a good thing to do to take a base model that has been optimized using ImageNet? I mean, all these models, the ResNets and the VGGs and the EfficientNets and so on, they have all been developed by trying to beat benchmarks on ImageNet. So is that actually a good thing to do? Because sometimes, I'm not sure if you have that, but we have it often, you take such a model and it completely sucks on the case you have. So we were wondering, well, might that be by design because you pick stuff that has been developed for something completely different? And I will not explain the plot now because I will explain it later. If you have started reading already, fine. I will just switch it away. What did we do? We adopted an experimental setting that became quite famous in the last few years, namely randomly generating a couple of neural network architectures, a couple of hundred neural network architectures, and see how they fare on different tasks. What we did, we took the AnyNetX family of networks. So from this, you get a lot of different neural network architectures. Not all architectures that work well in images, but most of them. You get all the standard AlexNets, all the VGGs, all the ResNets, all the RegNets, and so on. So a fairly large sample can be generated by modifying the hyperparameters of the AnyNet family. And we draw at random 500 such model architectures, different width, depth, heights, and other hyperparameters. And then we did the following. We selected all at least remotely interesting public data sets that have been used for benchmarking and publishing in computer vision that are not ImageNet and have at least some publications on them that are distinct from ImageNet, and tried two different things. First, we took each of our 500 architectures, trained it from scratch on ImageNet, tested on the respective test set, recorded the performance, and took the same architecture, trained it from scratch on one of these other 9 data sets. We only found 9 data sets that have at least a little community around them. There were a lot of them that are not public, that only have one publication and so on. So we took some that have a community around them, trained the architecture on the respective training set from these other cases, and then plotted the error. This architecture, each point here is one of these random architectures, the error it has on the test set of ImageNet versus the error it has when trained on one of these other data set on the test set of this other data set. So we wanted to see an architecture that has a specific performance in ImageNet. How does this architecture, when trained on the other data set, perform on ImageNet? And you see here a couple of statistics on these other data sets. You see also here samples of those. We have ImageNet over here. We have quite similar but a little smaller images here in the database called Natural. We have melanoma from, well, medical area. We have cracks in concrete from a basically industrial data set. We have here examples, where is it here, of pictures from power lines, power land lines. We have some bugs, the notorious CIFAR. Very different data sets, different size, different numbers of classes. What comes out of it? And we see here, for example, I mean, this is what we hoped for. We have the insects data set, which is this one. We see here error on ImageNet, error on insects, and we see here the correlation coefficient, which is close to 1, which is also what you see here. It basically means if an architecture works well on ImageNet, it also works well on insect. This is what you hope. I mean, this is why we all take stuff that has been developed on ImageNet, because we think this is a good proxy for whatever task we might have. But then other stuff is still quite okay. You still see the correlation coefficient here around 0.5. And then we have these 3 data sets. CIFAR 10, natural, power line. I'm not sure if you can read it. It's definitely not from the back, but these are negative correlation coefficients. Correlation of minus 0.1, minus 0.38, minus 0.4 something. That basically means, well, if you take something that works well on ImageNet, it means it will not work well on your task. At least if it is something like Powerline or Natural or CIFAR 10. So far, what we hoped we will not find, but found anyway, but potentially everybody suspected that will happen. So the interesting thing came when we started looking into what is actually happening here. So the general thing I don't think is very interesting. It basically just says, okay, an architecture that has been designed on ImageNet does not necessarily work well on whatever you have in practice. Okay, I guess we all suspect it. It's okay. The interesting thing is, first, how bad it actually gets, that it is negatively correlated. Well, this is really bad. And the other interesting thing is, okay, what are the influential parameters of the data sets? What actually makes a data set similar to ImageNet with respect to performance? First, and maybe you also suspect that we thought, well, the content of the images plays a role. ImageNet is typically, when I explain it to my students, I say, well, these are holiday pictures somehow, pictures you would take with a smartphone somewhere smaller than rectangular and so on. So what is closest to that is this natural image set. But natural really sucks. It's not similar to ImageNet in performance. Another thing we thought plays a role is the size of the images, because, well, neural network architecture, width, depth, it has to do something with size, doesn't it? I mean, if we have larger images, we need a higher capacity network, so we need a similar, well, not. So what we found out, the image-wise, the visual similarity or the size of the images actually plays not a huge role in determining if an architecture that is great on ImageNet is also great on the other data set. Interesting enough, what we found out is that the most important factor is the number of classes. ImageNet has, as you know, a lot of classes. We have the notorious 1,000 classes. And insects, that has the best correlation, has the highest number of classes from these other data sets. This work has been mainly done by my PhD student, Lukas Tugener, and what Lukas did then is he created subsamples of ImageNet, where he created an ImageNet 5, let's say, which has 5 classes, which basically meant he randomly selected 5 of the 1,000 classes and deleted the rest of the data set that didn't belong to those classes. And then he repeated these experiments. We see here CIFAR 10 versus ImageNet 10. And well, this is still not a great correlation, but it turned from a negative 0.5 almost to a positive 0.5. So basically, when you choose a neural network architecture that has been designed for some other task, the single most important factor, as it turned out in our experiments, is that the thing it has been designed for has a similar number of classes than your problem. Visual similarity, size of the images, just forget about it, but the important thing is similar amount of classes. if your task is a binary classification task, select an architecture that works well for binary classification and not for 1,000 class classification. Less interesting, but still an important thing, in the AnyNetX family, you have some of these hyperparameters refer to the block depth and the block width. And this block depth and width is are basically the two most important factors that you can vary in order to make the architecture fit to your problem. So the general depth and width of the neural network is also mostly tied to the number of classes you have in your data set. So I'm definitely happy we did that study. We wouldn't have suspected these, to find these things. We suspected that ImageNet is not the perfect proxy for everything, but we didn't suspect to find this correlation with the number of classes. Let's go into the second case. I guess you have heard of the Flatland challenge, but in case you haven't, I give you a very brief definition of the problem, how we saw it. So the problem is rescheduling of trains, and rescheduling is not scheduling. So it's not about creating the big, huge timetable of which train should be where, when. It's the more local problem of, well, my train has a delay of 1 or 2 minutes because somebody was late in opening the doors, entering the train. So we now have to fix this small problem of the train is 2 minutes behind schedule or something like this. And that's an optimization problem. In principle, you could optimize it in, so to say, closed form. Wouldn't it be for the enormous amount of things that could be done? Well, you cannot optimize it in closed form. It's just too many options to consider. So the Flatland environment, and you see a screenshot here of the visualization, is a task, a challenge where you can try out modeling each train as its own agent and test algorithms so the trains can find out for themselves how they should reschedule themselves and negotiate with the other trains. And there has been a challenge about it. Is there a current challenge?
Yes, it's recurrent for a few years.
And we participated in it, this time with another batch of students from our bachelor program. And, well, we didn't do too well. We didn't win the thing, but we found a couple of lessons learned. And then a very interesting thing that I come to on the next slide. So the first thing we noticed was, and of course, you know, when you work in RL, reinforcement learning is notoriously data hungry. It needs a lot of data, a lot of training in order to learn something. And we try to figure out, well, what kind of task knowledge can be incorporated into the learning so the learning task is eased a little bit. And you see an example here from the Flatland challenge, and here is our train. It's bound to go left. And well, you see there are not a lot of changes and signals and so on from here to here. So what's the point in deciding for every step here what to do next? It cannot do too much, right? It cannot turn left here, turn right here. It shouldn't go reverse. It's generally strange to go reverse on the track. So what we did is we incorporated task-specific heuristics, namely, well, when the track is just straight, there's nothing to do, just go straight until you hit the next, what is a Weiche? A switch, thank you. Until you hit a switch, and then you can issue the next decision. And that worked pretty well. It eased the learning task considerably to take out a lot of decisions, take away a lot of decisions from the agent that it actually does not have to take. And it improved the performance. This is how many of the trains actually reached their goal in the first round from, well, it doubled it basically. So that helps. And then interchange phase 2 of the competition, which is incorporates a lot more complexity. We reverted to a curriculum learning strategy where we didn't set the agents into complex environments from the first place, but started out with very simple levels here, They're small, not a lot of agents, only 4 on a small grid, not too many destinations, not too many different ways to reach a specific destination. Very easy task, and let them learn there for a while until they reached a success level of, let's say, 70%. And only when 70% of the episodes were played correctly, the agents were transferred to a second level, larger environment, more agents, more complexity, so to say. The idea was, well, the agent should learn some basic behavior of trains, how to behave well as a train in a simple environment, and only if they master that, go to the next level of complexity in order to, like we do it with school, with kids in school, right? Don't teach all the subjects from the very beginning. And it actually ensured a 6th rank. I'm not sure that this was super great, but at least the curriculum learning helped. Was a good thing in this competition. One thing we realized at the end is that potentially, if we do it a second time, we wouldn't use policy gradient methods again. Why? If you look at this image of a lot of tracks, switches, trains, train stations, there's a specific property here that my students called HighConsequence property. This is a high-consequence environment in the sense that if a single agent of the many agents on the same playing field makes a stupid decision at one point in time, like stopping in the middle of a track and blocking it forever, it basically means the episode is ruined. One really stupid decision ruins everything for everyone, not just for this agent, but for everyone. Nobody can potentially complete it. This is what they call high consequence environment. Some stupid actions have really high consequences for everybody. And now if you have a method that in the end gives you a stochastic policy, a policy where actions are taken with a certain probability distribution, just by chance, if you have a lot of actions to take and a lot of agents that are taking actions with a certain probability, just by chance, every now and then and every more often, you will have at least one agent just by chance taking such a stupid high consequence action, which is somehow not a good thing. We then tried another thing. We didn't look more into, okay, what other method then to use, but thought more about such a situation. And I'm closing with the analysis of this. You see here a train station and a train that is bound left, another train station and a train that is bound right, and those two trains should, in the shortest possible amount of time, reach their destinations. And as you see, of course, shortest amount of time is just go straight. And if we would be 2 human train drivers sitting in the left and the right train, we would probably need to negotiate. Okay, who is allowed to go straight and who's taking a detour? We would negotiate somehow, or somebody would have planned it for us. So how should rescheduling agents do this? How should they negotiate? How should they, what kind of course you could try to make up a rule like rechts vor links or whatever, but we pondered the idea, how can we make those agents negotiate? Does that actually work? So we came up with the following. Instead of just giving the agents actions to move, like go straight, stop, go left, go right, go reverse, we gave them 6 more actions, 6 communication actions. 5 of them free tokens, we didn't define any meaning, and 1 an end of transmission token. If both of them say after each other, communication is over. And now we created the rules of the setup as follows. Agents can learn to do any actions, and upon the first agent issuing one of the communication actions, the agents enter a communication loop. A communication loop means they are now not anymore in the mode of determining go left, right, straight. They are in communication. They're talking to each other, which means one is issuing a communication action, the first already started, and the next one now only has a choice between the 5 plus end of transmission communication actions until both of them directly after each other, issue the EOT, end of transmission. And then the communication loop is ended, and they can again choose any actions, what they want. They can talk again, they can also just go left, right, straight, stop, reverse. And again, we didn't enforce any meaning on these free tokens. We just figured, well, if you know computer science, you know we have an alphabet of 2 characters, 2 tokens, right, 0 and 1. And by a correct, a helpful encoding of zeros and ones, we can actually communicate whatever we want. We can have a Turing-complete language. We can encode everything in binary. So in principle, giving the agents the chance to have arbitrarily long conversations with 5 tokens, well, they could learn whatever they want, right? So let's see how it worked. And actually, that is a super interesting question in general I encounter in a couple of examples. Just that you give a learning system the ability to, in principle, learn something doesn't necessarily mean that they somehow really learn it, right? So this gives the agents the ability to talk whatever. But will it actually help anything? I mean, that's a complex learning setup, potentially. So what did we do? We gave the agents in the setup I just described a reward of -1 if after the conversation ended and they started driving again, they collided. We gave them a +1 if they didn't collide or didn't negotiate. And we designed it the way that the agent had no chance of knowing are they the first or the second, are they the left or the right, so they couldn't revert to something like, I'm the second agent, I'm always going left, I'm always taking detour. They couldn't do that, they didn't know who they are. We trained with 1 million episodes, we used A3C. And what we observed is, after this training, after enabling them to communicate, before only 47% of the trains in the setup I showed you arrived, which is roughly chance level, right? Chance if one takes a detour or not, and then if there's a collision or not. This increased to almost certainty that they arrived, 95%. So somehow communication helped. Somehow it increased from chance level to almost certainty. Then again, we did a very not yet too deep analysis of how the machine dialogues look like. And you see some examples here. So here, time steps, and this is always a 1 word and the reply. And 5 is the end of transmission action. We observed that there's a high diversity in this dialogue. There's not a single protocol, like one is commanding, I go first, and the other says, yes, please. It's somehow, we didn't see a lot of patterns in that, but somehow it managed to create these results. So what are the implications? It's still, well, yes. In principle, they could have learned something, a language, whatever. What it is, that is still to be found out. And rather than giving the typical summary at the very end, I want to end with a couple of questions for you to ponder when you go back to your machine learning cases. We observe it so many times. We work on a problem, and of course we have a goal in the project. We want to make it work. We want to win the challenge. We want to solve the business case. We want to beat the benchmark, whatever. And on the way to that goal, there are distractions. On the way to that goal, there are things that turn up that could be interesting, or they could be just a nuisance. And sometimes, like in the first case, we turn to these interesting things at the am Wegesrand, at the side, and look at them and found something very interesting, beautiful, a novelty, something that is really worth looking into and maybe writing about. And sometimes, like in the case of the machine communication, we see something like an emerging language, potentially, or not, who knows, and then find no time to look into it. But it might be worth, who knows, maybe something really, really interesting is happening there. You can take it if you want. I actually don't have a student looking into it. So maybe this is the same for you. And maybe it's a good thing to think about, well, of course, there's my actual goal, but maybe it's worth it looking into that interesting thing at the side of my track. That might be very interesting to look into. With this, thank you very much for listening.
Thank you very much, Thilo, for this interesting insights into two different areas. And of course, it was fun to hear the language research on Flatland that SBB was involved in. Very interesting. So now we're open for questions from the audience.
Thank you very much for your talk. I have a question about imbalances in classes. So you said, for example, you use this HAM 10,000 dataset from skin cancer. There's quite a big imbalance in classes in these datasets, and I can imagine that in some other one, how big was a role played by these imbalances in your results?
Thank you for the question. I think that's a very good question. I don't recall correctly. What I recall is that Lucas was actually doing a huge amount of ablation studies in order to control that we didn't miss anything. So because I cannot recall that this played a huge role, I assume he checked for that and it didn't play a huge role. But I would need to check to be certain.
Thank you, very nice talk. I was a bit curious about the train problem. It's really intriguing. So in the first one, you were saying you were doing some simple heuristic. Do you have like an assumption here that the trains have a constant speed or something? They cannot adapt to the others? Otherwise, it seems...
Yes, exactly. At that point, there was I think the rules were like they were having constant speed.
Okay,
so basically there actually wasn't much to decide, so we stripped the algorithm from choices that actually were non-choices.
Okay, but then in your second part, right, when they can communicate, then you relax that assumption, right? So they can communicate at any point in time, or do you keep that heuristic idea here?
They can initiate a communication any point in time. And basically, we assume that while they are communicating, that the world is not moving anymore. So basically, they can communicate, and in that tiny setup, basically, nobody else is moving. So while they're communicating, nobody else is changing positions. Yeah.
Okay, but it's still constant speed.
Yeah.
Okay, thank you.
I would have one question on the first part of your talk. If you could maybe elaborate a bit on the implications this has of the big vision of machine learning is in the future that it should generalize. That's why we want to do it, right? We don't want to train specific models. Currently we have to, but could you maybe elaborate a bit on that, what you believe? Is this just something we're not seeing, or is it a real blocker for generalizing models in the future?
I think it's a reminder that you have to take medicine at the right dose. I think it was a very lucky thing for the community to have the ImageNet competition, to have Krzyzewski's paper, and the vast success in 2012 on ImageNet, and then this established benchmark that basically drove development for a long amount of time. And at the same time, you see that overfitting to the data set or to the benchmark task is actually not doing a lot of good to downstream applications. So, of course, we all want to see generalizable models and methods, methods that work very well. And what this, I guess, reminds us of is that we cannot achieve that by only looking at one specific task, by only looking at one specific metric, by only looking at one specific thing. We have to, if you want to generalize to an unseen number of tasks and things, we also need to look at these unseen number of tasks and things. I think that's important.
Thank you.